thinking what to do. Oh! Yeah, look what I did. Oh, f***ing well.
So, after that apparently hyperbolic introduction, I hear you asking, what exactly is a pull-up resistor? And how is it that not having one could potentially lead to disaster? In this video, I will explain what a pull-up resistor does and explore the motivation for using them, and therefore why they matter so much. To explore this question, we will need to build a simple circuit on a breadboard and write a few lines of Python code to run some programs on a microbit microcontroller. All the required hardware is listed here. A breadboard with the microbit breadboard adapter, the microbit with its USB cable connected, a push button, a 10k ohm resistor, and of course jumper wires. And you will need the Mu Python editor for the microbit. First, plug in a single jumper into pin 0 and plug the free end temporarily into the breadboard away from the microbit to prevent it touching anything. Connect the USB cable to your computer and plug the other end into the microbit. In the Mu editor, click the plus to start a new program. Then copy the code labeled example analog underscore read.py and paste the code into Mu. If you don't have the code to copy and paste, just pause the video here and type in the code. Click the thumbs up button to check the code syntax. You'll know it's correct when you see the confirmation message. If there are errors, you'll need to fix the typing. Then press the flash button to download the program into the microbit. Once the confirmation message is shown, click the REPL button to look at the print log on the microbit. You will first need to manually click the reset button on the reverse side of the microbit to resume program execution. Then watch the screen for the bars of stars to continuously display on the REPL print log. Now unplug the free end of the jumper, which is the end away from the microbit, and using the bare jumper end, touch the ground pad on the adapter. Note that the stars go mostly blank. Then touch the bare jumper end to the 3-volt pad and watch all the stars appear. Lastly, touch the bare plug with your finger and note that the number of stars jumps around randomly. To understand what these observations mean, let's look at the circuit diagram. Firstly, what is clear is that touching the jumper to 3 volts or ground forces the input to the respective voltage. But the crucial observation is that when the jumper isn't connected to anything, or just connected to your fingers, the voltage at the input pin is very unstable. This is called a floating input, and it happens when an input isn't being forced to a fixed voltage level. Now let's see what can be done to fix this floating voltage. Returning to our circuit, this time we add the 10k ohm resistor between pin 0 and the 3-volt pin, and with the jumper safely away from the microbit, observe that the stars on the REPL window are full. This is because, while the jumper is not connected, the normal state, the input remains at the voltage of the positive rail because of the connection of the pull-up resistor, and this rail has the effect of opposing any external interference from influencing the input pin. Each time the jumper touches ground, the stars go to the minimum, and any time the jumper is floating, the maximum stars return. There is no uncertain voltage in between anymore. Note that there is a small current flowing through the pull-up resistor whenever the jumper touches ground. This is an unavoidable side effect to this solution to the floating voltage problem. But wait, why can't we just tie the input to the rail without going through the pull-up resistor? Why waste any power at all through the resistor? This is because when pressing the switch, we would then cause a short circuit across the rails, which is a very severe fault that could certainly reset the running program and possibly damage the microcontroller. Then why specifically choose a 10 k ohm resistor? Firstly, we don't want the wasted current to be too big, because when the button is pressed, the current flow just wastes power. So a 100 ohm resistor, for example, while still very effective at reducing floating voltages, will allow a large current to flow and waste quite a lot of power. Battery-powered devices in particular would quickly lose the charge using a 100 ohm pull-up. But on the other hand, if we reduce the power wasted by choosing a very large resistor, say a 10 megohm resistor, the speed at which the rail removes the external electrical noise is much, much slower because of the high resistance, which leaves the input still very vulnerable to the random variations of external voltages. We find in practice that pull-up resistors in the range of 10 k ohms to 50 k ohms work very well at reducing external voltages without wasting too much power when the button is pressed. Let's return to the breadboard again to attach the switch to the input with its pull-up resistor. This is the circuit we will build on our breadboard. Firstly, wire the 3V and ground voltage rails from the microbit pins. Now, add the switch, noting that its metal contacts are along these lines. Then jump a pin 0 to one side of the switch. Followed by the 10k resistor to the 3V rail. Lastly, jump the other side of the switch to the ground rail. That completes the circuit construction. Now we use the record log to view the bars of stars. And again, we note that the stars are nearly full. Unless the button is pressed, then they are nearly empty. But there is never any time when the input voltage is floating. Now we have built a push-button circuit that is not sensitive to external interference. To conclude our button build, we will paste the digital read program called example_digital_read.py into mu. If you don't have a copy of this program, you can pause the video and type it in now. Once you have checked for and corrected any errors, you can flash this new program into the microbit and go into REPL mode again. This time, you will note that the switch changes the message between the digital states true and false because we are using the read digital call in this program. This is how switches and buttons are designed in practice. And finally, the pull-up resistor has a counterpart, the pull-down resistor. This is the same as a pull-up resistor, except in this case the input is tied to ground using a resistor, and the button connects the input to the 3V rail instead of ground. The effect is to reverse the logic of the pull-up resistor, so that the input is false unless the button is pressed. And just one more thing before we finish. Many but not all microcontrollers have inputs with built-in pull-up and pull-down resistors that are selectable in software. The microbit is one of those microcontrollers. This line here allows the programmer to select pull-up, pull-down, and none for each input pin. This of course means that the external 10k resistor in our circuit build is entirely superfluous, but at least you now have learned why they exist and why they are so important. In this video, we have learned that digital input pins that are left unconnected are easily susceptible to external voltages, for example by just being touched. To solve this problem, these pins can be connected to a voltage rail through a resistor. If the input pin is tied to a positive rail, the resistor is called a pull-up resistor, and a resistor to the ground rail is called a pull-down resistor. This solution should remove any frustrations caused by the unreliable behavior of buttons and switches. Lastly, we learned that some microcontrollers, including the microbit, have internal pull-up and pull-down resistors that are software selectable. And that's all for this video. Thank you for watching. If you enjoyed this video or found it useful or educational, I would be grateful if you could hit the like button and also subscribe to my YouTube channel. I currently have 14 subscribers, and my lifelong goal is now to have 15 subscribers. So if you do decide to subscribe to my channel, not only would I be grateful, you yourself could have the satisfaction of being the one that allowed me to achieve my lofty ambition of 15 subscribers. In addition, should you feel like contributing a useful and constructive comment, that would be great as well. In any case, whatever you decide to do, please have a wonderful day.